Basically required to do 3 tasks, and I think I emailed you these tasks already. What it is in this practical, it is for you to become comfortable with everyday tools, i.e. pipettes. And you will use the graded pipettes. You have used them before, I guess. I think Rosalind showed you where you have this ball squeezy thingy bit on top of it, yeah? And how to read the grade on the pipette. You also will use the automatic pipettes. Did Rosalind show you those? Yeah, fantastic. Never, ever, ever, under any circumstances, use these pipettes without the tips. Yeah? Under no circumstances. These pipettes are fairly expensive. And if you use them without a tip, they are knackered. And we will reclaim the money from you. A set of pipettes is worth about 800 quid. Whew, yeah. I tell you what, I can think of a lot of things that I could do with 800 quid. Could you? Not really. So, well, if you are rich, I'm single. Okay. And this practical class is there for you to learn these things and also, again, to become comfortable with dilutions, because that is something that you're going to do, and also to be comfortable with presenting data. And we will discuss that in the second session, data presentation and data analysis. So it goes into the area of statistics. Who likes statistics? Hands up. Obviously not. Okay, wow. Who hates statistics? I tell you what, it's absolutely amazing what you can do with statistics. Sort of, I have a love-hate relationship with statistics. And did you know that 99.7% of all statistics are just simply made up on the spot? Yeah? So statistics is sometimes can be absolutely great because you can prove something and then somebody points out that this is complete and utter nonsense, and you say, oh, well, I can prove the opposite as well. So statistics is good. Anyway, this statistical analysis will be used to determine what is generally called the difference between accuracy and precision. And let me just quickly explain that. You've probably seen this picture before, yeah? What we try to do when we do anything in terms of measurements, and biosciences is all about measurements. Whether you measure how long a cancer cell lives, or you measure how long the tail of a mouse is, or you measure the number of molecules in a certain solution, it's all about measurements. And of course, what you want is this case here, where you're absolutely accurate and precise. And ideally, what you also want to do, if you repeat an experiment, that it is reproducible. Because if today the outcome is 25 millimeter for, foot length of a mouse, today is at 25 millimeter, tomorrow it's 125 millimeter, and on Wednesday it is 47 millimeter, it doesn't tell you anything. It just tells you that probably the way you measure things is not the right way. We can have precise measurements, that all the measurements are together, but they might not be accurate, because accurate would be here. You might have accurate, so overall you have sort of a distribution like that, but it's not precise. And when we talk about accuracy and precision, very often people mix them up. So in terms of bioscience lingo, they have a certain meaning. And of course, worst case scenario is you've got something like that here, when you are completely plastered and try to shoot something and it's all over the place. That's not what you want. So I want you to really be aware of the difference between accuracy and precision. So what are you going to do in your practical tomorrow? So the first thing that I want you to do is I want you to use these pipettes, and in order to do so, you are supposed to take measurements, repeat measurements. So you are supposed to take 3 tubes. You need to label them. So it would be very useful to bring along a marker pen. We do have a few marker pens, but usually that's sort of the limiting factor. And everybody's waiting till somebody has done their stuff with a marker pen. So if you have a marker pen, please bring them along. And don't leave them behind, because then you will never, ever see it again. So, and you are doing that, as far as I know, you are doing that in pairs, in twos. Yeah? So one person, for example, does the labeling of the tubes or the vessels, and the other person is preparing the solution or the pipette or something like that. And then you swap around, because everybody should have the opportunity to do the experiment. Okay, and I need to check that I get the right order of that. Okay, so the first thing that you do is you weigh the tubes on a balance. With the tube being empty. But if the tube has a lid, you weigh it with the lid. Okay? And you write down how much each tube weighs. Okay. You then add to each tube with the graded pipette, you add 1 milliliter for the A tubes. You add 2 milliliters for the B tubes. And you add 3 milliliters to the C tubes. Once you've done that, you weigh them again. So full. Again, with the lid. What you then do is you just simply calculate how much water have you actually put in. And you find that by just simply take the weight of the full minus the weight of the empty. What would be the units? Weight? Grams, exactly. So that would be in grams. And you get this, basically. You get data for that. Okay? So what you then also can do is you can calculate the mean. We will talk about mean in the second session. So you will calculate the mean. Bless you. You will calculate what is called the standard deviation. You will calculate the standard error of the mean. And again, if that is scary, wait to the second session, then it will become even more scary. Okay? You do that for the A tubes, for the B tubes, and for the C tubes as well. Okay? And then what you can do is you have used this graded pipette, pretty long. And I want you to do exactly the same experiment with the automatic pipette. And again, you have your tubes, A1, A2, A3, B1, B2, B3, C1, C2, C3. But this time they are very special tubes. In the first one, the tubes are, I think they are 4 milliliter tubes. And in terms of bioscience, 4 milliliters is quite a big tube, actually. Usually we do tubes in we do experiments in much smaller tubes. These tubes are called Eppendorf tubes. Bless you. Or lovingly called EPIs. Have you seen my EPI? If you ask that somebody in the venue, can I show you my EPI? They look a little bit like my drawing is terrible. Something like that. And they usually have a lid attached to them. So you just simply flip on the lid when you put something in. It's about the right size, yeah, these Eppendorf tubes. One of the big problems is that they have a round bottom, and this round bottom is to collect liquid easier instead of a square one. But of course you can imagine they don't stand easily. And therefore you need little racks with holes in them, where you just put your Eppendorf tubes in. So, okay, these are the Eppendorf tubes, and we've got loads of them. They usually hold about 1.5 milliliters. And in the A tubes, you put down, you weigh them again. Weigh empty. Then with your automatic pipette, you add 0.2 milliliter. This is the same as, how many microliters is that? 200? I heard 20 over there. Who thinks it's 200? Hands up. Who thinks it's 20? Hands up. Be brave. Nobody is brave. Well, it's right. He doesn't want to admit, hey? 200 microliters, right? And you can check that very easily with dimensional analysis. In the second one, you add 0.4 milliliters. How many microliters? Thank you. Not 40. And in the last one, you put 1 milliliter. And how many microliters? Thank you. 1,000 microliters. And again, you weigh your tubes with the liquid in it. So weigh full, not full, but with the liquid in it. You calculate the amount of water that you've added, so weight full minus weight empty. And you again calculate mean, standard deviation, and the standard error of the mean for A, B, and C tube. Okay? Happy with that? And then you obviously want to present the data somehow. The way we present data is usually through a chart. Very often people say graphs, and mathematically it's not absolutely 100% correct. But I don't care. Let's call these charts simply graphs. Yeah? And the graph that you need for this one here is you plot the volume of water that you added this is the stuff that you actually placed into your tubes, right? So it would be in, what would be the unit? Milliliter, exactly. This is the variable that is sort of independent because you decided what you want to put in. This is the independent variable. And the weight that you get is the dependent variable because it depends on what you put in. And you plot this against the weight of the water. And the unit here was, we said, grams. Yeah? So you probably have 3 milliliter here, 2 milliliter here, 1 milliliter here. And then you have something 0.2, 0.4, and then 1 milliliter here. Yeah? This is what it should look like. So 1 gram, 2 gram, 3 gram. So, and what you plot then is really your triplicates that you got. So for example, for the 3 milliliter, you measured 2.9, 3, and 3.1. Something like that. So it would look like 3 crosses on top of each other. And that would happen for each one of them, with one exception. Who is quick? Who thinks quick? 1 milliliter, exactly. Why? For 1 milliliter, there must be 6, because we have them in the graded pipette, and we also have them in the automatic pipette. And we can see which one is better. Yeah? So that would be your graph for that. Now, here are a few very, very important things. This is where students always fall down in exams. And I don't want that. Your graphs. Your graph is like your business card. It's absolutely essential that your graph looks good. Because have you ever seen somebody with a scruffy business card? They are not going to do any business. They are out before, just like that. So, there are a few things that I want you to bear in mind when you do a graph. First of all, your axes need to be labeled. I need to know what you plot here. What is it? Is it bananas? Is it volume of water? Is it lottery numbers? Absolutely essential. If you don't have that, the graph is null and void. It will give you 0 marks. Likewise here, for the dependent variable, again, it needs to tell me what the heck do I see here? What am I looking at here? Yeah? That's the one thing. The axes need to be labeled. The axes also need to be labeled with a unit. Is it liters? Is it microliters? Is it milliliters? Is it hectoliters? If there's no unit, the graph is null and void. Yeah? Likewise here. We will come to one exception where there is no unit on a graph, but that will be shortly after Christmas. So don't worry about it. No unit, no label, forget the graph. Right? Do we have an agreement? And the nicer your graph looks, the better it is. So it would be absolutely fantastic if you had something like a ruler or something. Because if you try to do a straight line, and it looks like that, it's not great, hey? So let's forget that. Straight line. Oh, I'm proud of my straight line. Right? So that's what it should look like. What I don't want you to do, sometimes I see that, is that people break the axes. That means they produce something like and then there's something like that. Yeah, something like that. Here is then, say, 1. Here is 100. And here is 200. Something like that. Do not do this. This is a criminal offense. Yeah? This is a criminal offense against any kind of graph. And it will result in total arbitrary numbers. It is as useful as a chocolate fire guard or, other useful things. Yeah? So don't use this broken thing. Completely no. Exactly. Yeah. Okay, are we clear what we are doing with that? Yeah? So I probably should do this one here. No, no, no. Okay, so that is the first experiment. Let's see what the second experiment is. Okay, in the second experiment, you are supposed to do some dilutions. And you start with a 0.5 molar stock solution. I think it is paranitrophenol. Is that right? Can you quickly draw paranitrophenol? Yeah? Okay, that's this guy. And it is colored. Yeah, it will absorb light. We will discuss absorbance and the use of a spectrophotometer in one of the lectures to come. At the moment, we are just concerned about diluting a solution of that. And so we have a stock solution, and you should prepare 3 milliliter of a 0. Is it a 0.5 molar solution? I doubt that. Sounds a bit high. Aha, millimolar. Sorry, I was 0.5 millimolar. Yeah, and you should prepare a 5 micromolar solution, 3 milliliters. So how much do you need to do? You want to quickly calculate that yourself? That's your stock, and that is your working solution. What would be the equation that you would need to use? Loud? C1V1, exactly, or the doctor and the pharmacist, yeah? So let's see. I can write 0.5 millimolar as 500 micromolar. It's the same thing. So I want 3 milliliter. This is the same as 3,000 microliter times 5 micromolar divided by 500 micromolar. Drip, 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 drip. So I need 30 microliter of this solution. But I want a total volume of 3 milliliter, so I need to add 2,970 microliter of the solvent. In this case, it is buffer, borate buffer. What this buffer does, again, let's not worry too much about it. We will discuss that in one of the later lectures. Yeah? So we prepare our solution, and actually we prepare that 3 times. Again, to measure our accuracy and our precision. So 3 times you do that. Okay? So you have 3 tubes with your 50 micromolar, with your 5 micromolar solution. Happy with that? And then you measure how much light is absorbed. And in order to do that, you use a spectrophotometer. That's basically a fancy machine that measures how much light goes through a solution. And again, we will do all the theory behind that in one of the next lectures. What you need to do in order to use the spectrophotometer, you need to have a sort of what is called a blank. And this blank is just simply a solution of your buffer. No nitrophenol in it. Just a solution. So first you have just 3 milliliter of your buffer. You measure that, and you press the 0 button. Press 0. That's fairly important because that sort of, it's a little bit like, yeah, when you use kitchen scales, yeah, and you put a sort of a pot on it, you always want to press 0 first, so that the weight of the pot is not counted. So everybody who cooks is pretty much familiar with this concept. So press 0 and then mix your stuff together, mix well, and then measure that stuff. So ideally what you should get is you should get measurement 1, measurement 2, measurement 3. And it will give you a certain reading. So 0.1, 0.11, 0.12. Right? Sometimes, if you're really good, it will give you 0.11, 0.11, 0.11. And people say to me, oh my God, this is terrible. I get 3 times the same thing. And I say, wow, that's good. It's not bad. It just shows that your measurement was very, very precise. They were all really close together. Yeah? So again, what I want you to do in this case is calculate the mean, calculate the standard deviation, calculate the standard error of the mean. Okay, are you happy with that? Yeah? You know what you're doing. So that's the second experiment. And there will be an extension to that, but I will deal with this extension after I've done the third experiment. The third experiment is basically exactly the same thing, but this time not with a substance that is colored. It is a substance that has no color, but still that absorbs some electromagnetic radiation. The substance is called bovine serum albumin. It is a protein. This protein is found in the blood, obviously, of cows. But there is also a human serum albumin available. This albumin is, albumins are usually globular proteins, more or less round-shaped, and they can transport all sorts of things. All sorts of things can stick to these proteins, and these proteins, with their load, then go through the bloodstream and deliver these things that stick to them to cells and other places. It is a molecule. This protein has a molecular weight of 66 kilodalton. And you know what this means? It means that 66,000 grams are in 1 mole. Or 1 mole is the equivalent of 66,000 grams. Okay? And again, you will be given a solution. What do we have? All right. We have a 10 milligram per milliliter solution. 10 milligram per milliliter, how many grams per liter? 10. Look. I cancel the M's out. Don't tell anyone. Right? It's between you and me. But this is just the easiest way. 10 grams per liter. Or how many grams do I have in 100 milliliter? I've got 1 gram in 100 milliliter. I just divide this by 10 and this by 10. Yeah? What's the percentage of this solution? It is a 1% solution, exactly. 1% weight per volume solution. I've just given you the answer to one of the comprehension questions, because I'm a nice guy. Okay, so you are supposed to make up 3 milliliter of 1 milligram per milliliter solution. So how many milliliter of this bovine serum? 10 milligram. So that's the stock. That's our working solution. How much do you need? Try to be faster than me. Got that? 300 microliter? Yeah? So you would need 300 microliter plus 2,700 microliter of buffer. And this time we use a different buffer. It is a phosphate buffer. Simply because bovine serum albumin doesn't like borate buffer. It will denature in borate buffer or do some stupid things. That's why we need a different solute in this case. Yeah? You do that, again, 3 times. You also do a 0 with pure phosphate buffer. And again, you measure 3 readings. Yeah? You are also supposed to do a 50-fold dilution. Oh, that's going to be hairy. So we started with a 10 milligram per milliliter. We put that to 1 milligram per milliliter. That was the first dilution. Yeah? How much did we dilute it? Loud? A tenth, exactly. So it was 1 in 10 dilution. Yeah? So a tenth diluted. Now we want it 50-fold diluted. 1 in 50. We just take for each 50 milliliters, we take 1 milliliter. So for this one here, that was the 1 in 10, we took 300 microliter. So for this one here, we take just a fifth of that, because that was already a tenth. I would do it another fifth. So we just simply take 60 microliters. Yeah? You think about it. So that's 60 microliter plus 2,940 microliters. Gives us, again, 3 milliliter. You zero it again with your phosphate buffer. And you do your 3 measurements. Okay, happy with that? Here comes a slight complication, because you have to be careful with the cuvettes. The cuvettes are the little things where you put your 3 milliliters in. And you take these cuvettes, they look a little bit like my drawing is absolutely awful, but you get the gist. They are usually made of plastic. They have 2 sides, 2 opposite sides that are clear, and 2 sides that are a little bit matte, or they've got something on it. You are, by law, only allowed to touch these things on the matte side. Don't touch them on the clear side, because the clear side, that is where the light goes through. Yeah? And if you have, say, nose picks, earwax, or God knows what, on your fingers, and you smear it over the clear side, then obviously the light can't go through your earwax or other disgusting things. So that's why they have specifically this matte side where you can easily touch it. So you basically put your solutions into these cuvettes. Be careful, touch it in the right thing, and then you put it in the right way into the spectrophotometer, and your demonstrators will show you how it has to be in there. Yeah? Now, for the first experiment, for the, where is it? For the nitrophenol, you can use any kind of plastic cuvette. For the BSA experiment, you have to have a very special cuvette that allows ultraviolet light to go through. And these cuvettes have a black dot. A black dot. They are labeled with a black dot. This means ultraviolet light can go through. Normal plastic cuvettes won't allow ultraviolet light to go through. So if you use the wrong cuvette for the BSA, nothing will happen. So watch out, for the BSA experiment, you need the one with the black dot. Are you happy with that? Yeah? I think I forgot that for the experiment with the paranitrophenol, you also need to do 3 milliliters of a 20 micromolar solution. So that would be 120 microliter of your phenol solution and 2,880 microliter of your borate buffer. Okay? Does that make sense? Any questions? So you know what you're doing tomorrow. It should not take you more than 1.5 hours. Right? Is everybody clear? God, I'm good. So we have a 10-minute break, and then we come back to a little problem that I introduced to you without you noticing it, okay? 10 minutes, back at 5 past.